Okay, hello everyone. Welcome back to the Colchin seminar. Today it's our pleasure to welcome Joris van der Hoeven, who will give a talk on yet another differential shape lemma.
Okay, well, thank you, Daniel. Thanks for the kind invitation. So yes, I will talk about this. Um, so this is joint work with Gleb Pogodin, who is also at my university at École Polytechnique. So let's see. Okay. So before I turn to the differential shape lemma, let me just recall a bit the classical shape lemma to you. Oh gee, hide video, hide meeting control. Okay, good. So I will, K will be a field of characteristic 0, and let's consider just a radical zero-dimensional ideal. So this is typically just a set of points in the plane. Okay, the variety of this ideal. And in general, generically, all the x coordinates of these points are different. Okay. So the vanishing polynomial of these x coordinates, which we see here, p of x, is in the ideal. Okay. And for every x coordinate, we also have a y coordinate. And we could just look at the interpolating polynomial of these points. Okay, so there's a unique polynomial q of degree smaller than the number of points, such that the images of the xi go to the yi. And then this means that basically y minus q of x is also an element of the ideal. Okay, so this is how you can basically describe a generic bunch of points in the plane, a finite set of points algebraically. So we have the ideal is going to be generated by two things, which are this polynomial p of x and this polynomial y minus q of x. And this is the generic situation for a radical ideal. Okay. Now, slightly degenerate could be that some of the projections on the x coordinate are the same, in which case we cannot directly associate a unique y coordinate to every point with a given x coordinate. So the form of this that we had on the previous page doesn't work anymore. But of course, what we can do is slightly twist our coordinates, like we see here, to make all the projections again different. So this is just a change of variables. The y coordinate remains the same. The x coordinate is just an affine transformation that we see here. And the classical shape lemma basically states that, yeah, this is always possible, and that radical zero-dimensional ideals are described like this. So here I focused on the two-dimensional case, so this actually works in any dimension. At the end of my talk, I will give some formulas for the general case, but just to keep things simple, let's mainly focus on the two-dimensional case where the formulas are a bit easier. Okay. So this classical shape lemma is actually due to Jenny and Mora in 1989, and this is a tool that is being used very much in computer algebra. It's a very useful description of zero-dimensional ideals. If we have an ideal that is no longer radical, this of course does not work anymore, because in that case basically our point set we may have some double points, some triple points, and so on, points with multiplicities. And in order to describe what happens in this case, we would have to look at the Grosvenor basis. So if you look at the lexicographical Grosvenor basis, when things are in shape position of the previous pages, then basically we will only have a line over here. But if we have multiple points, like in the non-radical case, then the Grosvenor base may have under the staircase we may have things that are a bit higher, like we see here. So all this is actually also well understood. So the shape of lexicographical Grosvenor basis in this case was described completely by Lazare in 1985. Right. So now let us go to differential equations. So let us first consider linear differential equations with constant coefficients. So basically, from an algebraic point of view, if we have two commuting derivations dx and dy, these are just symbols. So this is perfectly isomorphic to what we saw before, and of course we can look at an ideal on the left-hand side, and yeah, this also can be translated in an ideal at the right-hand side. But from a geometric perspective, things are a little bit different. Okay, so from a geometric perspective, on the left-hand side, we see the elements, the solutions of this ideal as points, a variety of points, like we see here on the left-hand side. And on the right-hand side, solutions of linear differential equations would typically be exponentials. So basically, for instance, the point 1, 1 would here correspond to something like e power x plus y, okay, which would basically the point 1, 1 satisfies the equations x minus 1 and y minus 1, which would here be something like dx applied to the function is equal to the function, and dy applied to the function is equal to the functions. So we get this solution. And of course, in the case of linear differential equations, we can take k-linear combinations. So I see them here as constants of these fundamental exponential solutions, and we get the full solution space of the linear differential ideal. Okay. So this point of view actually I think is kind of powerful, in fact, and not as known as it should be in computer algebra, because it's basically the bridge between commutative algebra and polynomial system solving and linear differential algebra, but still differential algebra. And basically for instance, things like Buchberger algorithm and Gröbner basis and things like this already existed on the right-hand side long before. For instance, Rosenfeld had exactly the concept of Gröbner basis with S polynomials and so on, are perfectly well described when you specialize them to linear differential equations with constant coefficients. Anyway, let's continue. So returning to the shape lemma, so the shape lemma stated that if we take a radical zero-dimensional ideal, that we can always find this simple change of coordinates, after which the ideal can be put in this shape position, that we have these polynomials p and q, such that the ideal is written like this. And just by translating this in terms of linear differential equations, we immediately get the thing that we see here. I made a slight modification here. As you see here, we had a change of variables for x and y. So if we want to just translate right away, we should have a change of derivations here. But this change of derivations is linear, so it is also induced by a change of variables. And yeah, we can see the formulas here. So this change of variables, we can put it like this, and this corresponds to the change of derivations that we see here just by looking at the inverse of the transpose of this matrix is this one. Okay, so perfectly isomorphic again, the two worlds. But now the next question is, can we actually make this a little bit more interesting in the linear differential case by not working over the constants, but working, let's say, over rational functions in x and y? Okay, in that case, of course, the coordinate functions do not commute with the partial derivations, dx and dy. So we're in a non-commutative setting in this case, and the ideals become left ideals. And if we want to have a similar, exactly similar statement as what we saw here, then of course we need to understand what it means, what a radical ideal means in the differential case. Okay? Here radical was just understood in the algebraic case, but we need to understand it differentially. So let us look what happens for something that is non-radical. Okay, so let's take again the same points, but let's make one of these points double. So okay, so the ideal, if we leave out the two that you see here, would just be the 3 points that we had before. But now I just squared the x minus 2 here, so this becomes a double point in the variety. And on the right hand side, what happens is that we then basically also get two linearly independent solutions. So one is still the e power 2x that we had before, but now we also have a second one, which we see here. So there is a polynomial and x and y coming in to describe it, and as it turns out, this always happens like that. If you have a multiple solution like the orange one here, then basically in the solution space, the corresponding exponential component, e power 2x, is getting a bit fatter. So you also get solutions that are this exponential multiplied by some polynomials and x and y. Okay. In particular, it means that in this non-radical situation, we have basically a basis of solutions, a k basis of solutions, but that this k basis is not just exponentials anymore. There are also these polynomial parts in x and y, and in particular, the basis elements here are not linearly dependent over the rational functions in x and y. Okay, so the inspiration of my talk actually came from the following theorem. Kowers, Kuchan, and Véron remarked that if we take this idea of being radical, this characterization that we see here in the linear, when we work over the constants, this is a characterization for being a radical ideal. If we just, in the case when we no longer work over the constants, take this as a definition of a d-radical ideal, then actually they proved that the shape lemma still works. Okay, so I was looking, I heard about this at the ACA, Applications of Computer Algebra, meeting that we had this year. And I thought, well, that's interesting to know. But at the same time, I was a bit, from a geometric perspective, I was a bit surprised because there is something a bit strange going on here. Because in fact, we have this concept of d-radical, which is basically being introduced by analogy to the polynomial, the commutative case, and it's actually used here to exclude some cases. They need this radicality to get the shape lemma. But in the differential setting, in fact, if you look to linear differential ideals from a differential algebra perspective, then actually all linear differential ideals are radical. Okay, so if we see, if we have a left ideal here in this ring, we can associate to it if f now is a differential indeterminate. So this is the ring of differential polynomials. Okay, so let's okay. But so yeah, so okay, we have it's a partial here. So okay, so we have all these these things. Okay. So we can associate the differential ideal that is generated by all the elements of this left ideal applied to our indeterminate, and we get we get actually a perfect differential ideal, which is always radical. Okay, so from this perspective, why do we want to introduce an artificial problem of that actually caused trouble for the shape lemma? For the shape lemma, non-radical ideals were a problem, and we somehow seem to introduce artificially introduce this problem. Actually, from a geometric point of view, I have always liked actually this distinction. Okay, from my perspective, this linear differential world actually describes ideals much better than in the purely algebraic case. Somehow the solution sets of these linear differential operators are more fine-grained than our geometric understanding in terms of point sets. For instance, let's look at the double point. Okay, so a double point at 0, well, it could be something like the ideal generated by x squared and y, but also x and y squared. In both cases, when you want to depicture this on a plane, it would be the point 0, 0, which you count double somehow, but you don't see how to count it double. On the other hand, in the linear PDE counterpart, all this becomes very clear, because in the first case, this would correspond to a solution which is x, and multiples of x become a solution. In the second case, multiples of y become a solution. So this actually describes the ideal much better. The solutions describe the ideal much better than just looking at it as a set of points. In fact, this can be made completely precise, this idea, by the linear differential Nullstellensatz. So if we introduce the space of all exponentials of alpha times x plus beta times y, where alpha and beta run over, the small constants, multiplied with polynomials and x and y, then we can look at sets of ideals of linear differential operators in this thing. Let's call the set of all ideals that we may have I, and we can also look at the corresponding solution spaces in this space F. Okay, so for every ideal, we can form the set of all functions in this space that vanish under all linear differential operators in the ideal. So we can see this as some kind of Zariski closed subsets of F, but in a linear differential understanding. And then, well, one can prove the following a bit folklore fact, but I could not actually find a precise reference to this. So basically, these two things are perfectly inverse in this case. Okay, so basically, to any ideal here. So I should have written it like this, I guess. Oh, what's going on here? Okay. Okay, let me do it like this. I have a lot of stuff from Zoom on my screen, which pops up at random moments. So this is sorry for the Sorry for that. Anyway, okay, so yeah, so to any ideal we can associate a corresponding zero set or set of solutions, and to any Zariski closed zero set we can associate the ideal of all operators that vanish on this thing. And basically these two maps are mutually inverse. So this is kind of a finer description of it's a finer kind of thing than Hilbert Nullstellensatz, which only works for radical ideals. But here basically we use the fact that that in the linear differential case, all ideals are basically radical from a differential perspective. Okay, and so we have this nice correspondence. Of course, in model theory, we know that we have this kind of correspondences because we could have replaced the space F here by some differentially closed field, for instance. But the nice thing here is that differentially closed fields are very hard to understand. We have no precise description of it. And for these linear differential things, we can do with something that is very concrete and very simple, actually. Okay, so that's the interesting thing here. Okay, so from this point of view perspective, it would be nice to have a shape lemma that fully acknowledges that everybody is radical in the differential setting. So okay, so can I get rid of this thing? Sorry, but okay, good. So let us again take a zero-dimensional left ideal. This time over k dx dy, where k is the field of rational functions here. So stating that this thing is zero-dimensional, this ideal basically is equivalent to stating that the quotient of the full ring of differential operators by I has finite dimension over k. Okay, and then the thing that the second differential shape lemma, the new differential shape lemma, can be stated as follows: that there always exists a polynomial such that if we consider this differential operator, so we have a dy as before, plus this polynomial times dx. So this time q that we see here is no longer a constant, it's a polynomial in y, but just a polynomial in y, not in the q does not depend on x, okay? And basically this operator, so modulo I, it generates the entire ring A. Okay, what is going on? So basically, so D, if we take its projection modulo I, okay, then this projection D bar and the powers of D bar basically generate A as a vector space, as a K vector space. In particular, since this quotient is finite dimensional over K, this means that there is some minimal polynomial. Okay, so let's say P. And also, since this thing generates everybody, the projections of dx and dy can also be generated. So there exist polynomials u and v such that dx can actually be written as u applied to d modulo I, and similarly for dy. Okay, so basically here we see, so it's slightly different than what we had as a shape lemma before. Okay, where basically we had one of these terms we didn't have it. Okay, but still it is very similar. Okay. So let me give an example. Okay, so it's interesting to look at an example precisely when the thing is radical. So here we take a quadruple point. Okay, dx squared dy squared. So the solution space of this thing is the constants. Then a basis of the solution is 1. We have x, y, and x times y. Okay. And all linear combinations of this are the functions. So this is a case, yeah, where the usual shape lemma does not apply. But what we will show is that if we take this derivation, okay, so dy plus y times dx, then actually this is going to generate a complete quotient space. So we really need this y to this coefficient here to depend on y. This cannot be a constant. If it were just a constant, we would be stuck as in the traditional case. So we're really making use of the fact that this y is not going to commute with the dy that is here. Okay, so let us see why this works. So we can look at the square of this thing. So we multiply it by itself and expand. So we have to be careful, of course, that if we apply dy to y, if we multiply dy with y, it becomes y dy plus 1. Okay, it's non-commutative. So if we do this, we get, if we just expand, we get this thing here. But now modulo I, these squares are 0. So it's just the right-hand side that we see here that remains. And we can remultiply this thing once more with d on the left. And expand a second time, and then again look what happens modulo I, and we find the following thing. And we do it a third time, sorry. So again we multiply this thing, and then we find that this thing is going to reduce to 0. But basically, if we look, so we do see that 1, d squared, d3 are linearly independent, so they basically generate everything because the quotient space was of dimension 4 here. And one can also rewrite dx and dy in terms of the multiples of d as a linear combination of d squared d3. Okay, we can check that here. Okay, so one can see that the ideal is basically being generated. So this shape position is going to be of the kind that we see here. Okay, so d4 is the minimal polynomial. That's just because everything we worked at 0 here. And then we have these other things. Okay. So dx expressed in terms of d and dy expressed in terms of d. Okay, so let me now try to do at least one proof in my talk. The proof is a little bit technical, but I hope that I will be able to convey some of the main ideas. Okay, so we have to find, let's just go back to the statement. Okay, so we have to find this this operator d, which is q times dx plus dy. Okay, so which generates everything. So basically it's all about finding a suitable polynomial q of y, and we can always assume that we take some polynomial q for which the dimension of what is generated by this d modulo I is maximal. Okay, and what we really want to show then is that if we take d in that way, well, that it basically generates everybody. So for this, let's introduce another derivation, which is d plus something else that I don't know yet, times dx. So if it does not generate everybody, I have to adjust this q. So I'm going to add something z. And for the moment, I'm just considering z to be some formal differential indeterminate in y. Okay, so it's differential, so it does not depend on x. So when I apply x to it's always 0, but I can apply dy and I can apply it I times, and they're all different because it's a differential indeterminate. So basically, yeah, the z prime, and so on are all algebraically independent here. Okay, it's just a formal indeterminate. And now we're going to consider this a bit complicated expression. So the exterior power of one, this twisted differential, and its powers up to degree m. And this expression, so I consider this over A, okay, over the ring A, so projected modulo I. And I can see this basically as differential polynomials in Z, this formal differential indeterminate, where I put all the coefficients on the right-hand side, because things may not commute in A, okay? And here on the right-hand side, we had some exterior powers here. So this lives actually in this exterior product that we see here. Okay, so this thing can be written like that. And the fact that we chose m to be minimal it basically means that when I plug in for z any other polynomial, okay, the dimension of this thing should not grow. So basically, these different things, when these different things cannot be all linearly independent, so they have to become zero. And so basically this omega vanishes at any polynomial, actually. Any polynomial. But if this happens for some differential polynomial, that it vanishes at all polynomials, then actually this thing has to be zero. Okay, so basically this a bit weird expression here has to be zero, which also means that if I expand it as a differential polynomial like this, that all the coefficients which are in this exterior product, they all have to be zero. Okay, and now the next idea is to go and focus on one of the coefficients of this expression, the one in z power, the m-1 derivative of z. Okay, so let us do that. So in order to do that, let us first look how the powers of this twisted differential operator d star look like exactly. So if we just multiply d star by itself and then expand it out, we see that there will be a z in front of the dx, and then some more stuff. So the leading thing would be of this kind, and by induction on R, when we do this several times, one can easily see that basically all these derivatives are of the form there is z, the r-1 derivative of z multiplied by dx, and then some other stuff where z the r-1 derivative of z does no longer occur. Okay, it only involves lower derivatives of z. And now if we take the coefficient of the differential monomial, the m-1 derivative of z in this thing, okay, so now we see that this m-1 derivative, the only thing where it can occur, basically, because of this relation here, is in the very last term that we see here. Okay, all these others, the highest one for m-1 was m-2, so this one doesn't occur. So if we want to look at the coefficient of this product, it's basically taking this coefficient in the last term that we have here, and we only have the monomials 1, so that is the part that does not depend basically on z at all in the other terms. So if we write that down, we get an expression like here. So this, if we take the part in d star that does not depend on z, it basically means that we set z to 0, so it becomes just d. So okay, so this one is just 1, then d, and so on until the ones that we have here. And by what we have seen here for r equal m, if we take the coefficient of this thing in here, we just get the dx. So the fact that this thing is 0 Okay, it means that we basically we have a dependency of dx in terms of all the things that we had here. So basically it means that dx is already generated by the powers of d. Okay, and if dx is generated, well, since d, the d that we see here, commutes with dx, basically dy is also in this thing. So basically the whole algebra is getting generated. Okay, so okay, this is a little bit technical, but this completes the proof. It's a bit analogous to one of the proofs of the how is it called, the I think the cyclic vector lemma. Okay, so let me now give a little dual interpretation of this result. So I stated the, let me go back. I stated this shape lemma in terms of a change of the derivations here. Okay. But as we saw already before, we can also look at changes of variables, and which induce that change of derivations. And since our change of derivations was particularly simple, it turns out that there's also a nice invertible polynomial change of variables, which we see here. So y, in this case, it's y that remains the same, and x is just changed as x plus some polynomial, and one can easily read this off from the formulas here. So here basically again we have this polynomial map, but if you look at the Jacobian and you take the transpose and then invert, you get the required change of derivatives that we see on the right hand side. Okay, so so basically there always exists a change of variables, so that if now we rewrite things in terms of the corresponding derivations in the new variables, then basically the whole algebra is generated by a single derivation with respect to the y. So we are basically back in traditional kind of shape position with respect to y. So let us go back once more to the example of this quadruple point. Okay, so we saw that the ideal was being generated by this derivation here, power 4, and then that dx could be expressed in terms of d modulo I and the expression of dy modulo I. Now, if we integrate this y that we needed in the change of variables, and we negate, so we get the one that we have here. If we look at this polynomial change of variables, then basically this is going to do exactly the same thing. So we do no longer need this one, but the d in this new, with respect to this new coordinates, just becomes the d with respect to y tilde, the new coordinate. And this looks really like the original shape position in the commutative setting, except that the coefficients, of course, are not necessarily constant. Okay. So, of course, all this can be generalized to higher dimensions. So just to finish my talk, I just give the statement here. So basically, in that case, the derivation that we need is going to be of the form that we see here. So basically, one of the derivations is, well, just dx1, and then the others are polynomials in x1 times the others. And dually, this corresponds to a change of coordinates that we can see here. Yes, so, and I thank you for your attention. This is the end of the talk as well.
Thank you very much for this very interesting talk. Are there any questions or remarks? Please just unmute yourself or write in the chat.
Yes, thanks for the nice talk. I was just wondering if there's anything you can say about the degree of those polynomials, Q and P.
It's exactly the dimension of A.
Okay.
Okay, this A. It's just let me go back. Okay, here the P that we have here is just the minimal polynomial of D, and since D generates everybody,
Okay.
it has to be its degree has to be exactly the dimension of A over K. So this is really like the classical shape lemma. So if we now go back, for instance, to this example, okay, here you can see it. So here we have something which is the degree is exactly the dimension of the solution space of this thing, and here we have dx minus something of degree at most 3. Here it had degree 3. The only difference with respect to the usual shape lemma is that the coefficients here are not necessarily constant. And the fact, if the thing was d-radical in the sense of the first shape lemma, then actually you can take constants here. But if you have something radical that is not d-radical, then necessarily you need something non-constant as the coefficients of these operators here.
Okay, thank you.
Further questions? Maybe I have a straightforward question while I'm looking at the chat also. So the original shape lemma for varieties, right? Commutative algebra, you have, let's say, two variables. You have one polynomial in X only, and then the other polynomial expresses Y. So from the perspective of solving, finding the points of the variety, you would say, okay, I factor my polynomial capital P, so find the roots of this univariate polynomial, plug into the other one, and you get the Y coordinates, right? Now,
Yes.
you discussed the exponential solutions in the differential case. Your shape lemma, does it allow something similar to find from your shape representation the solutions? Maybe that's straightforward. I don't know.
Factoring linear differential operators is not as easy as factoring polynomials.
Yeah. So that's why I'm asking. Yeah.
But in principle, I mean, algebraically speaking, at least the structure is similar. So if you can factor, so let me go back to this other thing. Okay, so indeed, if you can factor the kind of operator that we see here, of course, this is going to it means that you will be able to factor the ideal I as well. Okay, so you still have to see what happens on the blue the blue parts, but you're definitely going to be able to write your ideal as an intersection of simpler ideals, which are all in this nice shape position. Okay, the shape position is going to be preserved, I think. So basically, in terms of solving, this would mean that basically you're going to first solve in this y tilde, and once that you have the, let's see. Yeah. I'm not sure that one can as easily say, I just first solve in y tilde and then take the x parts, right?
Yeah, it was just an idea.
That is a bit, I think, not really how it works here. But definitely, I mean, a factorization of this operator will introduce nice factorizations of the ideal I. That for sure.
Yeah.
And of course, you also have the other thing is that a factorization does not necessarily mean that you can write it as an LCM of lower order things. Okay, here this is actually kind of already a counterexample. Okay, so if you can write it as lower order things, you get a nice. You can see it as a nice intersection, but in general it will be. Yeah, you have a factorization, but it will just be a right or a left factor. But still, I mean, factors of this thing will induce factors of I. That's for sure.
Yeah. Very good. Yeah. So okay, it was not as straightforward. Yeah. Are there other questions? Please just unmute yourself if you have a question. If this is not the case, we thank Joris again for this very interesting talk.